All right, we're now into the home stretch, the last two sections of the course. So, the first two sections of this unit, 9.2, 9.3, they dealt mainly with exponential functions and graphs and then logarithmic functions and graphs. However, with logarithms, we also have a couple of properties that are specific to logarithms. All right, so first things first, though, before we even get into those properties, we have what's called the change of base formula. Because if you noticed on your calculator, you only have two buttons, right? One that says log, which would be your common log, which we said last time, of course, was base 10. And you also had your natural log button, which was the ln button, and that would have been log base e, right? So ln is base e, right? And natural log, common log was written just log, right? And that was base 10, and then natural log was ln, which was base e. So since those are the only two buttons on the calculator, we really need to evaluate inexact logs of other bases, right? So what do I mean by that? I mean something like, all right, well, what is log base 5 of 8, for example, right? Because I know that log base 5 of 5 equals 1, right? So I know this for sure. And I know log base 5 of 25 equals 2, right? So you know that. But what you don't know is what is precisely log base 5 of 8. We don't know. But we do know that because of this change of base formula, it says that the log base a of x can be written either as a base 10 log or a base e log, right? Either as a common log or a natural log if I just take the log of x divided by the log of a, or the ln of x divided by the ln of a. So in other words, if I want to evaluate this on the calculator, I can say, all right, well, log base 5 of 8 is really log base 10 of 8 divided by log base 10 of 5. And then I can get an approximation for it on the calculator, right? All right, so if I open my calculator, I can do log 8 divided by log 5. And we know that from what we said before, this should be between 1 and 2, a lot closer to 1 than 2. So it's 1.292, right? So this would be approximately 1.292, right? So that's using change of base formula. I mean, and it works even if I use natural log. I can change to natural log base also. So like I could have said that that is also the same as ln of 8 divided by the ln of 5, and I'll get the same value, right? I still get my 1.292. So whether I use base 10 or base e, I'm going to get the same value, right? So I'm not really going to belabor that because that's just a simple formula, right? And actually, on a side note, some people who have newer calculators, like 84 plus and one that was made in the last few years, might actually have a log base button, and they don't even need to use this. If you have a log base button, it would be under the math menu. It would be, I think it's letter A. See, you see how this calculator, this is like the original TI-83. It only goes up to 0, so it goes from 1 through 0. The newer ones also have like A, B, C, D, and I believe if you have an A option under the math menu, it's actually log base, and then you can actually enter log base 5 of 8 or any base log on your calculator. So that's just a little side note. And if you have that button, you can avoid having to do change of base formula. So just take a look at your calculator, see if you have it, because you might. All right. So now we get into the other properties, right? The more substantial properties, which would be the product rule, the quotient rule, and the power rule. Now the product rule and the quotient rule and the power rule, really, all three of them come from the fact that a logarithm is really an exponent. So if you recall, when you had something, an exponential expression such as x squared times x to the fourth, what did you do when you were multiplying these like bases together? You would take the two exponents and you would add them together. So this would have given you x to the 2 plus 4, which is x to the 6th. And that's precisely what this power here is telling you. that if you have the log of a product, right, the log base a, right, which just means any base of a product, calling it here mn, right, it's equal to the sum of the individual logs. And that's sometimes how this rule would be stated. It would be stated as the log of a product is the sum of the logs, right? Sometimes that's what you would hear. If this rule is going to be written in words, that's really what it's saying. The log of a product is the sum of the logs. So if you had something like the log base 10, this is, right, of 1000x, right, that's really a product. So you're thinking of the m as the 1000 is like your m, and the x as your n. So this is the log of a product. So it's really the sum of the two individual logs. So it's the sum of the log of 1000 and the log of x. But the nice thing about this situation here, of course, is that the log of 1000 is exact. It's just 3, right? Because 10 to the third is 1000. So this is 3 plus the log of x. Okay? So you can write the log of 1000x as 3 plus the log of x. Right? So it's a pretty straightforward rule. And again, it comes from your exponent rules. And it's the same thing with this quotient rule, right? This quotient rule that we have here, which says that the log of some quotient, right, in this case m divided by n, is really the difference of the two logs. And again, that's how this one would be written. This would be written as the log of a quotient is the difference of the logs. So another similar example to the last one, say you had the log of, actually log base 4, let's say, of 64 over y, right? Log base 4 of 64 over y. So in this case now, the 64 is your m, and the y is your n. So by my quotient rule, this is just the log base 4 of 64 minus, right, it's the difference of the two logs, so minus the log base 4 of y. And just like in the last situation, log base 4 of 64 is the exact value, right? 4 to the third power will give you 64, so this is really 3 minus the log base 4 of y. Okay, so that's how that one would simplify. So that's your quotient rule. And then, of course, the third one is what's referred to as the power rule. And I skipped the exponent portion of that, of the explanation in the last one. But again, if you recall exponent rules, remember when you had something like x to the third to the fourth? So if you had a power to another power, what did you do with those powers? You actually multiplied them. So in this case, x to the third to the fourth would be actually x to the 12th, right? Because it's 3 times 4. This is the same idea. You have the log base a of something, but it's raised to a power. So remember, log base a of m is like an exponent. So really what you have here is like an exponent to another exponent. So what do you do when you have that scenario? You multiply the power times the log, right? So something like this would be, I don't know, log base 2 of 4 to the 9th, right? Because, oops, a situation like this, would you want to do 4 to the 9th? No, because 4 to the 9th is some huge number, right? So in this situation, the 4 is your m, and the 9 is your r, right? And a is 2, because that's always the base. So this is going to be equal to, by my rule, I bring the power, which is the 9, out front, and I multiply it by the log base 2 in this case of m, which here is 4. So it's 9 times log base 2 of 4, which in this case is just 9 times log base 2 of 4 is just going to be 2, because 2 squared gives you 4. So this is 18, right? And this example really shows the value of using that rule, because again, if I had done 4 to the 9th first, I'm going to get some huge number. And I'm not going to know that 2 to the 18th power is that huge number, right? So that's a situation where it actually made it doable by hand because I used the power rule. All right, so those are my 3 main rules, along with the change of base formula. Okay, and I'll do another video that'll just give you some more complex problems that are going to combine all 3 rules into one, right? Because none of these problems that I showed you here, none of these examples combine the rules. So we'll do some of those combining rule problems in the next video.